damp, mouldy homes are a reality for nearly half of New Zealand. 49% of us live in homes that are either damp or have visible signs of mould, often in the most deprived parts of the nation. The simple fact is, the cost of either renovating or heating a home is too high for thousands. Moisture in the home is truly inevitable. It comes from many different sources, such as cooking, cleaning, showering, drying clothes, and even breathing. The average person creates 500 millilitres of water vapour every day simply by breathing. This may not seem like a lot, but this means that a family of 4 every day creates 2 litres, the equivalent of 1 standard-sized milk bottle. This just goes to show how truly unavoidable moisture in the home is. And what makes these damp homes worse is when they aren't properly insulated. When this is the case, the tenants are quite often hesitant to open windows to get in much needed dry, but cold air, especially in winter. This creates a damp, stale environment, which is a perfect place for mould to grow. When mould grows, it releases airborne allergens and, in the worst case, toxins. These allergens and toxins, when they come into contact with the body's eyes and mucous membranes in the nose, throat, and respiratory tract, cause symptoms such as coughing, wheezing, nasal congestion, and chest tightness. For the majority of healthy adults, this poses no major threat. However, for the young and for the old, the consequences are far worse. Every single year, 30,000 children are hospitalised. The rates of asthma in New Zealand are over twice that of the global average, 1 in 9 compared to 1 in 20. We spend $145 million unnecessary dollars per year on health issues caused by these damp homes. But worst of all, 1,600 people die every year or every winter prematurely solely because of how damp their homes are. This is simply unacceptable. The previous national government has tried to fix this, but to no avail. The current Labour government is currently up in the air with what their housing policy is. Just last week, they announced that they were changing the Kiwi Build scheme, which said they would build 100,000 affordable homes in the next 10 years because this was unrealistic. As a result, they've instead decided to give some of those funds to first-time home buyers. But this doesn't fix the problem that there are still thousands of homes that are damp, and so thousands will die if we don't do something. My solution to drying these homes is using a cotton material that has been coated with a polymer PNI PAAM. This material is extremely hydrophilic and hygroscopic, meaning it absorbs water vapour right out of the air. So much so that it absorbs 340% of its own weight in water vapour. And what's more, as this material is essentially a cotton sheet, it can be shaped into anything. For example, the shape of a paper towel roll. This can easily be moved around the house, as well as there will be a high surface area to volume ratio, meaning that the rate of water absorption, or the rate of water vapour absorption, would be very high. And so the aim would be to have, on average, each home getting 2.5 kilos of this material, as this would be able to absorb 8 litres of water vapour, which is the daily amount produced by a family of 4. Now, of course, this doesn't need to come in one large 2.5 kilo roll. In fact, that wouldn't be ideal because it would be impractical. Instead, if we gave still 2.5 kilos of this material, however, in many smaller rolls, families would be able to dry multiple rooms at once and to differing capacities simply by putting more rolls into one room compared to another. For example, you could dry a baby's room more than their parents' room. And so you might be thinking to yourself, okay, this is great. We're drying these homes, but won't we have tons of wet cotton that's very hard to dry? Well, fortunately, we won't, because this PNI material is extremely special in the sense that at 32 degrees Celsius, it undergoes a stark chemical change to become extremely hydrophobic, and so it dehydrates. So at 32 degrees Celsius, and this change occurs at 32 degrees Celsius, which is the lower critical solution temperature, or the LCST. So below the LCST, the PNI polymer prefers to form intermolecular hydrogen bonds. This is between the PNI's amide groups and the water molecules. This reaction has a negative enthalpy because bonds are being formed. At the same time, the water molecules are nicely arranging themselves around the PNI's amide groups, as seen here. This means we've got a negative enthalpy, but also a negative entropy. As such, if we substitute a negative enthalpy and negative entropy into the general Gibbs free energy equation up here, and we cancel out these two negative signs, we find that the Gibbs free energy equation has a plus T delta S term, where temperature is the absolute temperature in Kelvin, and delta S is the magnitude in the change of entropy. This means that for a high enough temperature, we get a positive Gibbs free energy, and this reaction is no longer spontaneous, and so it no longer occurs. And then also at the same time, once the PNI is above this 32 degrees, it prefers to form intramolecular hydrogen bonds. This is between adjacent amide groups, and so the water molecules are unable to bond to this PNI polymer. And this process is completely reversible, meaning that once the PNI is back below 32 degrees Celsius, it can once again reabsorb all this water. And then, just as a note, the drying process is incredibly fast. We can see here, this is a single strand of the PNI treated cotton at 16 degrees Celsius, fully saturated with water. And then as it progressively warms, we can see that it dehydrates until at 36 degrees, this is essentially completely dehydrated. So now that we have a solution, or now that we have a way to dry these homes, how do we dry these homes? Well, as the housing crisis disproportionately affects those who are most deprived within New Zealand, it would be unfair to expect individuals to burden the cost of these rolls and their subsequent drying. So as a result, we should set up a socialised system which is similar to the LPG bottle swap, where at community centres, analogous to petrol stations, we have large warming ovens, where families bring in their wet rolls, put them into the ovens, take some dry ones home with them. So how will these ovens work? Well, at this stage, there is a plan to have a hole through the centre of these rolls. This is so that there's a higher moisture absorption rate, but this means we can also put prongs onto the back of the ovens, similar to a test tube drying rack, where we can place the rolls onto and maximise space usage within the oven. Then also, of course, we're going to need some method to dispose of this wastewater. Fortunately, this could be as simple as a hose out of the back of the oven, because the water that comes off of the PNI material is clean, it's in fact drinkable, so it can simply be directed into a garden. So we have a solution. Now, is this economically viable? Well, it will be economically viable if it costs less than the previously mentioned $145 million per year, as we can assume that the health costs, or the health spending caused by these damp homes, will decrease significantly. So, in New Zealand, as of last year, there were 1.2 million homes. About half of these were damp. So this means we need 600,000 2.5 kilo units of this material. At the same time, we need to figure out how many ovens do we need. Well, we can assume that most of these damp homes are in deprived areas within New Zealand. We can assume they're mostly in the 5 most deprived deciles in New Zealand, which consists of 900 census unit areas, which is approximately equivalent to one community. So if we then buy 20 pre-existing industrial ovens and implement these modifications I previously mentioned, we should only spend about $20 million. This is because we'll be buying 18,000 ovens, and these pre-existing industrial ovens cost a bit less than $1,000. So then, of course, with the cost for modification, this price will come up, but we can round it to $20 million. And so this means if we ignore running costs for this stage, we have $120 million left. Now, so we need 600,000 units of this 2.5 kilo material. Unfortunately, this PNI treated cotton isn't yet commercially available, so a precise cost isn't known. However, in an article, it has been quoted as cheap. Only adding the polymer to this cotton only increases the cost of the cotton by a small fraction. And so this means we have a maximum budget of $200 per roll, and as there's cheap, this should be more than enough. So those are the startup costs. They're doable. Now, what are the running costs? Well, we have 18,000 ovens. These are all rated to a maximum power output of 1.2 kilowatts per hour. If they were to all run at this maximum power output for an entire year, we would use 1.9 times 10 to the 8 kilowatt hours of energy. If we were then to buy this at the expensive rate of 35 cents per kilowatt hour, we would spend $66 million. Please note this is a maximum running cost. And so overall in the first year, the government will be making a net loss. This is because the health costs will be on top of the startup costs and the running costs. However, in subsequent years, once we no longer have these startup costs and this health cost on the health spending begins to reduce, we should start saving money. But most importantly, there will be a marked increase in the health and quality of life for thousands of New Zealanders simply because they have drier homes. The reality is, New Zealand has damp homes and they are harming us. This PNI treated cotton will dry these homes. So all we need to do is buy this cotton and these ovens, and a warmer, drier, but most importantly, healthier future will be a reality for thousands of New Zealanders. Thank you.
Thanks, Louis. Aren't houses being insulated?
Yes, they are. However, the current stand by the government is very loose wording. So only floor and ceiling insulation is required if it's easy to implement. So for example, any homes with solid concrete foundations, they don't have to have floor insulation because it's impractical to implement this insulation. And then roof insulation by itself, while is better than no insulation, isn't a lot because you do lose a lot of heat through the windows and through the walls.
And would this not be more expensive than simply equipping people with a dehydrator machine and paying for the power cost?
No, so if we assume that we need to also buy the dehumidifiers, a dehumidifier that removes a similar amount of water, so costs about $400 or $500. So if we're then to buy 600,000 of these, this would be $240 to $300 million just in obtaining the dehumidifiers. And then dehumidifiers of that size cost about $30 to $40 per month to run. So we can see the dehumidifiers are a lot more expensive than this method.
What's PNI used for right now?
So it's currently an experimental polymer in this sense. It's being applied to collect water in arid environments for agriculture. So in various places, for example, the Namibian desert, where at night it's very cold, less than the 32 degrees, and there's a very high humidity, the PNI will absorb this water, and then during the day the sun will heat up the PNI treated cotton, and the water will simply fall right out. So this is used for agricultural purposes. It could also be implemented into survival clothing for the desert, as it's non-toxic to contact with the skin.
No toxicity involved either in its manufacture or its subsequent use?
In its subsequent use, no, I cannot comment on its manufacture, as it's still reasonably experimental at this stage, as in there are ways to manufacture it, but no mass production yet.
Thank you.
Thank you.